And now in this lecture we'll answer two questions. In the first question, we will find out the area of this green shape. In the second question, we will find out the length from this line segment PQ is equals to x. We have to find out the value of x. So we start with the first question. In the drawing, we have a circle inside this big semicircle. In addition, we know that this is line segment AQ, that equals to 4 units in its length. This is line segment TB, that equals to 1 unit in its length. This is angle STB, that is a right angle. This is angle PQA, that is also a right angle. Again, our test is to find out the area of this green shape. So first of all, we will define the radius of the big semicircle as x and the radius of the small circle as y. So write it down. X is the radius of the big semicircle. And y is the radius of the small circle, according to our definition. In addition, we define the center of this small circle. This point is point O. Likewise, we define the center of this big semicircle. This point is point C. We will also define the point of tendency of tangent AB with this small circle. This point is point N. We define the point of tendency of tangent ST with this small circle. This point is point L. We define the point of tendency of tangent PQ with this small circle. This point is point H. And finally, we define the touching point of the small circle with the big semicircle. This point is point K. In the next step, we will join points O and N together by a straight line. Point O is the center of the small circle, point N is the point of the small circle itself, therefore ON is the radius of this small circle, that equals to y units according to our definition. The radius ON that equals to y, the radius ON is drawn to point N, that is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius NO. If AB is perpendicular to NO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees, according to rule 1. We know that this is angle PQA, that is the right angle according to what is given in the question. AB is the diameter of the semicircle. AB is the diameter, it is absolutely a straight line. So if we focus on the upper side of the straight line AB at point Q, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 states that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of the straight line AB at point Q? We have this angle that is the right angle, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. Likewise, this is angle STB. It is a right angle according to what is given in the question. So if you focus on the upper side of the straight line AB at point T, here the sum of the angles must be equal to 180 degrees according to all three. So which angles we have the upper side of AB at point T? We have this angle that is a right angle, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to all three. Therefore, this missing angle must be equal to 90 degrees in its size. In the next step, we join points O and L together by a straight line. OL OL is of course the radius of this small circle that is equals to y according to our definition. The radius OL that is equals to y, the radius OL is drawn to point L, that is the point of tendency of tangent ST with this small circle. And whenever you have a radius that is drawn to the point of tendency, then tangent ST will be perpendicular to the radius LO. If ST is perpendicular to LO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to the sum rule, rule 1. So actually, inside the quadrangle OLTN, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrangle is equal to 360 degrees. And therefore this fourth missing angle must be equal to 90 degrees in its size. So inside quadrangle OLTN, we have 4 right angles, and according to rule 5, any quadrangle that has 4 right angles must be at least a rectangle if not a square. So we relate to quadrangle OLTN as a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So rectangle OLTN, side OL must be equal to the opposite side NT. But OL is y, therefore the opposite side NT must be also equal to y units in its length. NT equals to y. We repeat on the same process on this side of the drawing. That is to say, we will join points O and H together by a straight line. OH is of course the radius of this small circle is equals to y. The radius of OH is drawn to point H, that is the point of tendency of tangent PQ with this small circle. And whenever you have a radius that is drawn to the point of tendency, then tangent PQ will be perpendicular to the radius edge O. If PQ is perpendicular to edge O, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees, according to the sum rule, rule 1. So in quadrangle edge O and Q, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. 270 degrees plus the size of this fourth missing angle, in total it must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrangle is equal to 360 degrees. And therefore this fourth missing angle must be equal to 90 degrees in its size. So inside quadrangle edge O and Q, we have 4 right angles, and according to rule 5, any quadrangle that has 4 right angles must be this rectangle for the square. So we relate to quadrangle edge O and Q is a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle edge O and Q, side edge O is equal to the opposite side NQ. But edge O is y, therefore the opposite side NQ must be also equal to 1 unit in its length. This is line segment QT. Line segment QT is part of the diameter AB. Again, line segment QT is part of the diameter AB. AB is a straight line, and therefore QT must be also a straight line. Because part of a straight line must be also a straight line. So QT is a straight line, and therefore QT in total must be equal to QN, that is y, plus NT, that is also y. So QT in total must be equal to 2y. Already known, QT, line segment QT, equals to 2y units in its length. AB is the diameter of the semicircle. The radius of the semicircle is x, therefore the diameter must be equal to 2x. Okay, so that is known. The diameter AB must be equal to 2x from one side, but from the other side, AB is equal to 2x is also equal to AQ plus QT plus TB. Again, AB in total equals to AQ plus QT plus TB. So I write it down. AB in total equals to AQ plus QT plus TB. So repeat again. From one side, the diameter AB is twice as long as a radius, therefore it is equal to 2x. But from the other side, the diameter AB also equals to AQ plus TB. The diameter AB also equals to AQ plus QT plus TB. So AB that equals to 2x in total equals to AQ is 4 plus QT. We just right now found out that QT in total equals to 2y plus TB. TB equals to 1 unit in its length according to what is given in the question. So in total we found out that 2x equals to 4 plus 2y plus 1. So 2x equals to 2y, 4 plus 1 is 5. So 2x equals to 2y plus 5. Here we subtract 2y from this equation, and we get that 2x minus 2y equals to 5. Here we take 2 as a common factor out of those two expressions. So inside the brackets we have x minus y. So 2 times x minus y equals to 5. Here we will divide this equation by 2. And finally we get that x minus y equals to 5 over 2. That is 2.5. So in total we found out that x minus y equals to 2.5. What is the length of the missing line segment CN? From the drawing it is very easy to see that CN in total equals to CB minus NT minus TB. Again, CN in total equals to CB minus NT minus TB. So I write it down. Cn equals to Cb minus NT minus TB. Again, I should find out that Cn equals to CB minus NT minus TB. So Cn in total equals to CB. Point C is the center of the semicircle, point B is the point on the semicircle itself, therefore CB is the radius of the semicircle, that is equals to X. Minus NT. NT equals to Y. Minus TB. TB equals to 1. So in total we should find out that Cn equals to X minus Y minus 1. So Cn equals to X minus Y. X minus Y equals to 2.5. Therefore, we substitute X minus Y here by 2.5 minus 1. So in total, Cn equals to 2.5 minus 1, that is 1.5. So in total, we should find out that the length of the short line with Cn is equal to 1.5 units. So actually, this is the short line segment Cn is equal to 1.5 units in its length. Cn equals to 1.5 units. So in the drawing, the small circle touches the big semicircle here at this point, point K. So we have here internal notch between the small circle and the big semicircle. And whenever we have an internal notch between two circles or semicircles, we can implement rule 9. So I'll put quickly on rule 9. According to rule 9, if two circles touch each other internally, then the straight line that connects their circles together passes for their touching point. In the drawing, we have two circles. The center of the big circle is at point O. The center of this small circle is at point M. The straight line that connects their circles together is of course the straight line OM. And according to this rule 9, the straight line OM must pass for their touching point, that is point P. Again, according to rule 9, the straight line OM must pass for point P, that is their touching point. Or, in other words, OMP is one straight line. Again, OMP is one straight line according to this rule 9. So we can actually implement rule 9 in our drawing. Why? Because in our drawing, as I already mentioned before, we have an internal notch between the small circle and the big semicircle, and this point, point K. The center of the big semicircle is at point C. The center of the big semicircle is at point C. The center of this small circle is at point O. The straight line that connects the centers together is of course the straight line CO. And according to rule 9, the straight line CO must pass for their touching point, this is actually point K. Again, according to rule 9, the straight line CO must pass for point K, that is their touching point. So we join point C and O together by straight line, and according to rule 9, the straight line CO must pass for their touching point, that's actually point K. You can see in the drawing that the straight line CO indeed passes for their touching point, that's actually point K, exactly according to rule 9. So according to rule 9, COK is one straight line. Again, according to rule 9, COK is one straight line. If COK is one straight line, it means that CO must be equal to CK minus OK. Again, CO must be equal to CK minus OK. So write it down. CO equals to CK minus OK. So CO equals to CK. CK is the radius of the semicircle is equals to X minus OK. OK is the radius of the small circle is equals to Y. So in total, if we found out that CO, the length of this line segment CO equals to X minus Y. But we already found out that X minus Y equals to 2.5. So we can substitute X minus Y here by 2.5. So CO, the length of line segment CO is 2.5. We already found out that the length of line segment CN is 1.5. And ON is the radius of the small circle, that is Y. So in the next step, I'll copy the right angle CON in a new page and we will implement the Pythagoras theorem on this right angle times CON. According to the Pythagoras theorem, in any right angle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here by PT is the relation for Pythagoras theorem. So actually, this is the right angle OCN that according to the original drawing. This right angle OCN, according to the Pythagoras theorem, OC squared, that is the square of the hypotenuse, equals to ON squared plus NC squared. So I write it down. OC squared, that is the square of the hypotenuse, equals to ON squared plus NC squared. OC is 2.5, therefore OC squared is 2.5 squared, that is 6.25, and it is equals to ON squared. ON is Y, therefore ON squared is Y squared, plus NC squared. NC is 1.5, therefore NC squared is 1.5 squared, that is 2.25. So in total we found out that 6.25 equals to Y squared plus 2.25. Here we will subtract 2.25 from this equation, and we get that 6.25 minus 2.25 is 4, so 4 equals to Y squared. Here we will take a root out of this equation, and finally we get that Y, the radius of the small circle Y, equals to the square root of 4, that is 2. So if we found out that the length of the radius of the small circle Y is equals to 2 units. We already found out that x minus y equals to 2.5, but y is 2, so x minus y is x minus 2 equals to 2.5. Here we will add 2 to this equation, and we get that x equals to 2 plus 2.5 is 4.5. 4.5 is 9 over 2. So if you found out that the radius x of the big semicircle is equals to either 9 over 2 units in its length, or in terms of numbers, the radius of the big semicircle, x equals to 4.5 units in its length. Our task is to find out the area of this green shape. So what is the area of the green shape? From the domain, it is very easy to see that the area of the green shape in total equals to the area of the big semicircle minus the area of the small circle. Again, the area of the green shape in total equals to the area of the big semicircle minus the area of the small circle. So it is now the area of the green shape in total equals to the area of the big semicircle minus the area of the small circle. The radius of the semicircle is x, and therefore the area of the semicircle must be equal to pi x squared over 2. Minus the area of the circle. The radius of the circle is y, therefore the area of the small circle must be equal to pi y squared. So in total, we found out that the area of the green shape equals to pi x squared, that is the area of the semicircle, minus pi y squared, that is the area of the small circle. So it is equals to pi over 2 times x squared. X is 9 over 2, therefore x squared is 9 over 2 squared. Minus pi y squared. So it is minus pi, y is 2, so y squared is 2 squared, it is 4. So in total, we found out that the area of the green shape equals to y over 2 times 9 over 2 squared minus 4 pi. Here we will open the brackets of this expression and we get that pi over 2 times 9 over 2 squared. 9 over 2 squared equals to 9 squared, that is 81. Over 2 squared, that is 4. Minus 4 pi. In the numerator of this expression, we have 81 pi over 2 times 4 is 8. Minus 4 pi. Here we will multiply minus 4 pi by 8 and then we'll divide it by 8 in order to have a common factor with this expression. So minus 4 pi times 8 is minus 32 pi divided by 8. 81 pi minus 32 pi is 49 pi over 8. 49 pi over 8 is 19.24 square units. So she found out that the area that we're looking for in this question, that is the area of this green shape, it is equal to either 49 pi over 8 square units in its size. In terms of numbers, it is equal to 19.24 square units in its size. So we finish with the first question. In the next step, I'll present to you the second question and we'll solve the second question of this lecture. In the second question, our task is to find out the length of this line segment PQ, the length of this line segment PQ, that equals to x. We have to find out the value of x. So, in the drawing, we have a semicircle. We know that point O is the center of this semicircle. This is line segment OS. That equals to 2 units in its length. This is line segment SB. That equals to 1 unit in its length. PT equals to TS. Again, our task is to find out the length of this line segment PQ that equals to x. We have to find out the value of x. So, in the first step, we complete this semicircle to a circle. We completed the semicircle to a circle, and we will extend line segment TS by third line until it touches the circle. We define the touching point of the extended line segment TS with this circle. This point is point M. And we will join points P and M together by a straight line. By doing all those constructions, we can do periphrangal PTM. According to what is given as the equation, periphrangal PTM equals to 90 degrees in its size. And periphrangal PTM subtend on chord PM. Again, periphrangal PTM subtend on chord PM. So here we can implement all 5. I'll repeat quickly on all 5. According to rule 5, any peripheral angle that is equals to 90 degrees must subtend on the diameter of the circle. In the drawing, we have a circle. This is peripheral angle MAN that is equals to 90 degrees in size. And therefore, according to this rule 5, peripheral angle MAN must subtend on the diameter of this circle. And indeed, peripheral angle MAN subtend on MN, that is the diameter of this circle. So according to rule 5, any peripheral angle that is equal to 90 degrees inside must subtend on the diameter of the circle. We can implement rule 5 in our drawing. Why? Because in our drawing we have peripheral angle PTM that is equal to 90 degrees inside, and therefore according to rule 5, peripheral angle PTM must subtend on the diameter of the circle. Peripheral angle PTM subtend on chord PM, and therefore according to rule 5, chord PM must be the diameter of the circle. So it is now, if we found out that chord PM is the diameter of the circle according to rule 5. It is given us the question that point O is the center of the circle. So point O is the center of the circle, point P is the point on the circle itself, therefore OP is the radius of this circle. OB is also the radius of the circle. OB equals to OS plus SB. So OB equals to OS, that is 2, plus SB, it is 1. 2 plus 1 is 3. Therefore, the radius of the circle equals to 3 units in its length. The radius of P equals to 3, and the radius of M also equals to 3 units in its length. In the next step, we'll do a construction. That is to say, from point S, we'll draw perpendicular on the diameter PM. Again, from point S, we'll draw perpendicular on the diameter PM. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point S and the diameter PM. This point is point N. By doing this construction, we can deduce the small right triangle O and S. Those two angles, they are defined as vertex angles, and you know that vertex angles are equal to each other. So if we define the size of this angle as alpha, then the size of this angle must be also equal to alpha because they are equal to each other. So in the right triangle ONS, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. Likewise, in the upper right triangle PQO, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha, according to the same rule that states that the sum of the angles in any triangle is equal to 180 degrees. It is very easy to see that the upper right triangle PQO is similar to the lower right triangle N and so, according to angle similarity rule. That is to say, those two angles are both equal to alpha, therefore they are equal to each other. Those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees, and therefore they are equal to each other. So if we found out that all the angles of the upper right triangle PQO are correspondingly equal to all the angles of the lower right triangle OSN. And therefore those two right triangles are similar to each other according to angle similarity rule. So already known, we actually found out that the upper right triangle PQO is similar. This is the sign of similar to the lower right triangle ONS according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side NS of the right lower triangle OSN over side PQ of the upper right triangle, triangle PQO equals to side OS of the right lower triangle, triangle ONS over side PO of the upper right triangle, triangle PQO. If in again, from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side NS of the lower right triangle ONS or side PQ of the upper right triangle PQO is equal to side OS of the right lower triangle, triangle ONS or side PO of the upper right triangle, triangle PQO. NS is the missing side, so we leave it as it is. Over PQ. PQ is the line segment that we are looking for in this question, and it is equal to x. So actually, we have to find out the value of x. So PQ is x, and it is equal to OS. According to what is given as the question, OS equals to 2 units in its length over PO. We already found out that PO is the radius of this circle. That equals to 3 units in its length. So in total, we actually found out that NS over x equals to 2/3. Here we will multiply this equation by x, and we will get that the missing side NS equals to 2x over 3 or 2/3 x. So this is the missing side line segment NS that equals to 2/3 x. Write it down. And S equals to 2/3 x. In the next step, we define this angle as beta. So in the green triangle, the green small triangle, S and M. This angle equals to beta, this angle equals to 90 degrees, and therefore this first missing angle must be equal to 90 degrees minus beta. Why? Because 90 degrees minus beta plus beta is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. Likewise, in the big right triangle PTM, this angle is beta. Therefore, angle beta is the common angle that belongs to both triangles. Angle beta belongs to the green triangle NSM, and angle beta belongs also to the big right triangle, triangle PTM. So this angle is beta, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus beta according to the sum rule. Then the sum of the angles in any triangle is equal to 180 degrees. It is very easy to see that the big right triangle PTM is similar to the small right green triangle, triangle NSM. That is to say, this is angle beta, that is the common angle that belongs to both triangles, so you can write down that angle beta equals to itself as a common angle that belongs to both triangles. So what I mentioned before, angle beta belongs to the big right triangle PTM, and angle beta of course belongs to the small green triangle, triangle NSM. In addition, those two angles are both equal to 90 degrees minus beta, and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees, and therefore they are equal to each other. So if you prove that all the figures of the big right angle PTM are corresponding equal to all the figures of this small green right angle NSM. And therefore those two right angles are similar to each other according to angle similarity rule. So write it down. We have found out that the big right angle PTM is similar to this small green right angle SNM according to angle similarity rule. And for the fact that those two right angles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side NS of the green small right angle SNM over side PT of the big right angle PTM equals to side SM of the green right small triangle SNM over side PM of the big right triangle PTM. It is given us the question that PT equals to TS. So if we define the length of side PT as A, then the length of side TS must be also equal to A because they are equal to each other. So if you found out that from the fact that those two right angles are similar to each other, the following relationship exists between their sides. Side NS of the green small right triangle SNM over side PT of the big right triangle PTM is equal to side SM of the green right triangle SNM over side PM of the big right triangle PTM. We have already found out that NS equals to 2/3 x. Over PT. According to our definition, PT equals to A units in its length. And it is equals to SM. SM is the missing side, so we leave it as it is. Over PM. We have already found out that PM is the diameter of the circle. The radius of this circle equals to 3, therefore the diameter must be equal to 6. So PM equals to 6. So in total we should found out that 2/3 x over A equals to SM over 6. Here we will cross multiply this equation and we get that two-thirds x times 6 equals to ASM. This will be equation 1. If we found out after we cross multiplied with equation 1, we found out actually that 2/3 x times 6 equals to ASM. 6 over 3 is 2, and 2 times 2x is 4x. So in total this expression equals to 4x. So 4x equals to ASM according to equation 1. In the next step, I'll repeat quickly on rule 15, and we'll implement rule 15 in our drawing. We already talked about rule 15 in the previous lectures, so I'll repeat on it quickly. According to rule 15, if chord AB intersects with chord CD at point O, then the following equation is true, that AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. So the drawing you have a circle. This is chord AB that intersects with chord CD at point O. So in this moment, the following equation is true, that AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. So we can implement rule 15 in our drawing. Well, put in our drawing, we have chord TM that intersects with chord AB at point S. Again, chord TM intersects with chord AB at point S. So actually, all the requirements of rule 15 are satisfied, and therefore we can implement rule 15. So I write it down. Actually found out that in our original drawing, chord TM intersects chord TM intersects with chord AB, and the intersection point occurs at point S. So according to rule 15, the following equation will be true, that TS times SM equals to AS times SB. And again, according to rule 15, the following equation will be true. TS times SM equals to AS times SB. TS is A according to our definition. SM is the missing side, so we leave it as it is. And it is equals to AS. AS in total equals to AO plus OS. AO is the radius of the circle that is equals to 3, plus OS that is 2. So in total AS equals to 3 plus 2, that is 5. Times SB. SB equals to 1 according to what is given to the question. So in total, according to equation 2, we found out that A times SM equals to 5 times 1. 5 times 1 is 5, so In total, we found out that according to equation 2, A times SM equals to 5. This is according to equation 2. While according to equation 1, we have only found out that A times SM equals to 4x. So according to equation 1, we found out that A times Sm equals to 4x. So we have two equations for the same expression ASM. Therefore, we create equation 3 that says that ASM according to equation 1 must be equal to ASM according to equation 2. According to equation 3, ASM according to equation 1 must be equal to ASM according to equation 2. ASM according to equation 1 equals to 4x, and it must be equal to ASM according to equation 2. ASM according to equation 2 equals to 5. So in total, according to equation 3, we found out that 4x equals to 5. Here we will divide this equation 3 by 4, and finally we get that x equals to 5 quarters. 5 quarters is 1.25. So we found out that PQ is equals to x is equals to either 5 quarters units in its length, or in terms of numbers, it is equals to 1.25 units in its length. So repeat again, we found out that the length of this line segment PQ is equals to x, it is equals to either 5 quarters units in its length, or in terms of numbers, PQ is equals to x is equals to 1.25 units in its length. So we finish with the second question. In the next step, I'll summarize the lecture. We'll start with the first question, of course. In the first question, our task was to find out the area of this green shape. So, in the drawing, we have a circle inside this big semicircle. We know that this is line segment A cubed, that is equals to 4 units in its length. This is line segment TB, that is equals to 1 unit in its length. This is angle STV, this is right angle. This is angle PQA, this is also right angle. Again, our task is to find out the area of this green shape. So first of all, we define the radius of this big semicircle as x, and the radius of this small circle as y. In addition, we define the center of this small circle, this point is point O, and we define the center of this big semicircle, this point is point C. AB is the diameter of the semicircle, therefore it must be twice as long as the radius. The radius is x, therefore the diameter AB must be equal to 2x. We define the point of tendency of tangent AB with this small circle, this point is point N. Likewise, we define the point of tendency of tangent ST with this small circle, this point is point L. We define the point of tendency of tangent PQ with this small circle, this point is point H, and finally we define the starting point of the big semicircle with this small semicircle, this point is point K. In the next step, we join points O and N together by straight line. Point O is the center of the small circle, point N is the point of the small circle itself, therefore ON is the radius of this small circle, this is equal to y according to our definition. The radius ON is equal to y, the radius ON is drawn to point N, that is the point of tendency of tangent AB with this small circle. And whenever your radius is drawn to the point of tendency, then tangent AB will be perpendicular to the radius NO. If AB is perpendicular to NO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. This is the angle PQA, that is the right angle according to what is given as the question. AB is the diameter of the semicircle, therefore it is absolutely a straight line. So if we focus on the upper side of the straight line AB at point Q, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 says that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of the straight line AB at point Q? We have this angle that is the right angle, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. In the next step, we join points O and H together by straight line. OH is of course the radius of the circle, the radius of the small circle, that is equal to y. The radius OH is drawn to point H, that is the point of tendency of tangent PQ with this small circle. And whenever your radius is drawn to the point of tendency, then tangent PQ will be perpendicular to the radius HO. If PQ is perpendicular to HO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to the same rule, rule 1. So in quadrilateral OHQN, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle, in total it must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this fourth missing angle must be equal to 90 degrees in its size. So inside quadrilateral HOQN, we have 4 right angles, and according to rule 5, any quadrilateral that has 4 right angles must be this rectangle and plus a square. So in order to quadrilateral HONQ is a rectangle because it has 4 right angles. But we also know that the opposite sides of an rectangle are equal to each other. So an rectangle HO in Q, side HO must be equal to the opposite side QN. But HO is right, therefore the opposite side QN must be also equal to 1 unit in its length. Repeated on the same process on this side of the drawing, that is to say we join points O and L together by straight line. OL is the radius of the circle that is equal to y, the radius OL is drawn to point L, that is the point of tendency of tangent ST with this small circle. Whenever the radius is drawn to the point of tendency, then tangent ST will be perpendicular to the radius LO. If ST is perpendicular to LO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees, according to the same rule, rule 1. It is given the question that this is angle STB, that is a right angle. So AB is a straight line. So if you focus on the upper side of the straight line AB at point T, here the sum of the angles must be equal to 180 degrees according to rule 3. So which angles we have at the upper side of the straight line AB at point T, we have this angle that is 90 degrees, plus this missing angle, in total the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore this missing angle must be equal to 90 degrees in its size. So inside quadrilateral LT and O, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this fourth missing angle must be equal to 90 degrees in its size. So inside quadrilateral ONTN, we have 4 right angles, and according to rule 5, any quadrilateral that has 4 right angles must be this rectangle and plus a square. So we relate to quadrilateral OLTN as a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So rectangle OLTN, side OL must be equal to the opposite side TN. But OL is right, therefore the opposite side TN must be also equal to 1 unit in its length. QT is a straight line because it is part of the straight line AB. Part of a straight line must be also a straight line. So QT is a straight line, and therefore QT in total must be equal to QN plus NT. So QT equals to QN, that is Y, plus NT, that is Y. So in total QT equals to 2Y. So AB is the diameter of the semicircle, therefore it is equals to 2x from one side, but from the other side, AB also equals to AQ plus QT plus TB. Again, AB also equals to AQ plus QT plus TB. Then again, from one side, AB is the diameter of the semicircle, therefore it is equals to 2x. From the other side, AB also equals to AQ plus QT plus TB. AQ is 4, QT is 2y, and TB is 1. Again, AQ is 4, QT is 2y, and TB is 1. So in total, 2x equals to 2y, 4 plus 1 is 5. So in total, 2x equals to 2y plus 5. Here we substitute 2y from this equation and find out that 2x minus 2y equals to 5. Here we took 2 out of this from those two expressions, so inside the brackets we left with x minus y. So 2 times x minus y equals to 5. Here we divided the equation by 2 and found out that x minus y equals to 5 over 2, that is 2.5. So x minus y equals to 2.5. What is the length of this short line at Cn? From the drawing it is very easy to see that Cn in total equals to Cb minus Nt minus Tb. Again, Cn in total equals to Cb minus Nt minus Tb. And again, Cn in total equals to Cb minus Nt minus Tb. So Cn equals to Cb. Cb is the radius of the semicircle, that is equals to x. Minus Nt is y, and Tb is 1. So in total we found out that Cn equals to Cb, that is x, minus Tn, that is y, minus Tb, that is 1. So in total, Cn equals to x minus y minus 1. X minus y is 2.5. So we substitute x minus y by 2.5 minus 1. 2.5 minus 1 is 1.5. So in total, we found out that the length of the short line square Cn is equals to 1.5 units. This is Cn, that is equals to 1.5 units in its length. So in the drawing, we have an internal line between the small circle and the big semicircle, that is to say they touch each other internally at point K. And whenever you have an internal line between two circles, you can implement rule 9. So if it click on rule 9, according to rule 9, if two circles touch each other internally, then if two circles touch each other internally, then the straight line that connects the centers together passes through their touching points. So in the drawing we have two circles. The center of the big circle is 0.0. The center of this small circle is 0.m. The straight line that connects their centers together is of course the straight line OM. And according to this rule 9, the straight line OM must pass through their touching point, that is point P. Again, according to rule 9, this rule 9, the straight line OM must pass through point P, that is their touching point. Or OMP is one straight line. Again, OMP is one straight line according to rule 9. So we can implement rule 9 in our drawing. Why? Because in our drawing, as I already mentioned before, we have an internal line between the small circle and the big semicircle at point K. The center of the big semicircle is at point C. The center of the small circle is at point O. The straight line that connects the centers together is of course the straight line CO. And according to rule 9, the straight line CO must pass through their touching point, that is point K. Again, the straight line CO must pass through point K, that is their touching point. Or COK is one straight line. COK is one straight line. So if COK is one straight line, it means that CO must be equal to CK minus OK. And CO must be equal to CK minus OK. CO equals to CK minus OK. So CO equals to CK. CK is the radius of the semicircle, that equals to X, minus OK. OK is the radius of the small circle, that equals to Y. So in total, CO equals to X minus Y. The length of this line segment CO is X minus Y. But we already found out that X minus Y equals to 2.5. Therefore, the length of line segment CO is 2.5. We already found out that Cn equals to 1.5 units, and On is the radius of the small circle, that equals to Y. So in the next step, by copying the right triangle OCN in the equation, we implemented the Pythagoras theorem, on this right triangle, triangle OCN. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Usually, this is the right triangle OCN that according to the original drawing. In this right triangle OCN, according to the Pythagoras theorem, OC squared, that is the square of the hypotenuse, equals to ON squared plus CN squared. OC is 2.5, therefore OC squared is 2.5 squared, that is 6.25, and it is equals to ON squared. ON is y, therefore ON squared is y squared, plus NC squared. NC is 1.5, therefore NC squared is 1.5 squared, that is 2.25. So in total we should find out that 6.25 equals to y squared plus 2.25. Here we subtract 2.25 from this equation, and finally found out that 6.25 minus 2.25 is 4, so 4 equals to y squared. Here we took out this equation, and finally found out that y equals to the square root of 4, that is 2. So if we found out that the radius of the small circle y equals to 2 units in its length. We already found out that x minus y equals to 2.5, but y is 2, therefore x minus y is x minus 2, that is equals to 2.5. Here we added 2 to this equation, and we found out that x equals to 2 plus 2.5, that is 4.5. 4.5 is 9 over 2. So the radius of the semicircle equals to either 9 over 2 or 4.5 units in its length. Our task is to find out the area of this green shape. The area of this green shape equals to the area of the big semicircle minus the area of the small circle. And again, the area of the green shape in total equals to the area of the big semicircle minus the area of the small circle. The radius of the big semicircle is x, therefore the area of the big semicircle, must be equal to pi x squared over 2 minus the area of the circle. The radius of the small circle is y, therefore the area of the small circle must be equal to pi y squared. X is 9 over 2, therefore x squared is 9 over 2 squared. So in total this expression equals to pi over 2 times 9 over 2 squared minus pi y squared. Y is 2, therefore y squared is 2 squared, that is 4. So in total this expression equals to 4 pi. We open the brackets here, and we should find out that this expression in total equals to pi over 2 and times 9 over 2 squared. 9 over 2 squared is 9 squared, that is 81, over 2 squared, that is 4. So in total this expression equals to 81 pi over 2 times 4, minus 4 pi. So we have in the numerator of this expression 81 pi over 2 times 4, that is 8, minus 4 pi. Here we multiplied 4 pi by 8, and we multiplied minus 4 pi by 8, and then we divided by 8 in order to overcome factor of this expression. So minus 4 pi times 8 is minus 42 pi divided by 8. 81 pi minus 42 pi is 49 pi divided by 8. So if you found out that there of this green shape, that is there that we are looking for this question, is equals to either 49 pi over 8 square units in its size. So in terms of numbers, the area of this green shape equals to 19.24 square units in its size. So we finish with the first question. The next step, I present to actually the second question, and we solve the second question of this lecture. In the second question, our task was to find out the length of this line segment PQ is equal to x. We have to find out the value of x. In the drawing, we have a semicircle. Point O is the center of the semicircle. We know that PT equals to TS. This is angle PTS, that is the right angle. This is angle PQS, that is also a right angle. This is line segment OS, that is equals to 2 units in its length. This is line segment SB, that is equals to 1 unit in its length. Again, our task is to find out the length of line segment PQ, that is equals to x. We have to find out the value of x. So in the first step, we completed the semicircle to a circle, and we extended line segment TS by a straight line until it touches the circle. We define the touching point of the extended isometric with this circle. This point is point M. In the next step, we join points P and M together by a straight line. By doing all those constructions, we get the peripheral angle PTM. Peripheral angle PTM equals to 90 degrees in its size. And according to rule 5, any peripheral angle that is equals to 90 degrees in its size must subtend on the diameter of the circle. Peripheral angle PTM subtend on chord PM, and therefore according to rule 5, chord PM must be the diameter of the circle. Point O is the center of the circle. Point B is the point of the circle itself, therefore OB is the radius of the circle. OB in total equals to OS plus SB. So OB equals to OS, that is 2, plus SB, that is 1. So OB in total equals to 2 plus 1, that is 3. So the radius of the circle is 3. The radius PO is 3, the radius OM is also 3. In the next step, we did the construction, that is to say from point S, we do perpendicular on the diameter PM. Again, from point S, we do perpendicular on the diameter PM. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point S and the diameter PM. This point is point N. By doing this construction, you can do write small triangle ONS. Those two angles are defined as vertex angles, and we know that vertex angles are equal to each other. If we define the size of this angle as alpha, then the size of this angle must be also equal to alpha because they are equal to each other. So in the right triangle ONS, this angle equals to alpha, this angle equals to 90 degrees, and therefore this first angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees it equals to 180 degrees, that is the sum of the angles in a triangle. Likewise, in the upper right triangle PQO, this angle equals to alpha, this angle equals to 90 degrees, and therefore this first angle must be equal to 90 degrees minus alpha, according to the sum rule that the sum of the angles in the triangle is equal to 180 degrees. In the next step, we prove that the upper right triangle PQO is similar to the lower right triangle ONS, according to angle similarity rule. That is to say, we put those two angles, they are both equal to alpha, therefore they are equal to each other. Those two angles are both equal to 90 degrees, and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha, and therefore they are equal to each other. So if we prove that all the fares of the upper right triangle PQO are corresponding equal to all the fares of the right triangle ONS, and therefore those two right triangles are similar to each other according to angle similarity rule. And again, if you found out that the upper right triangle PQO is similar to the lower right triangle ONS according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We will derive that side SN of the lower right triangle ONS over side PQ of the upper right triangle PQO is equal to side OS of the lower right triangle ONS over side PO of the upper right triangle PQO. We derive that side NS of the lower right triangle NS over side PQ of the upper right triangle PQO is equal to side OS of the lower right triangle ONS over side PO of the upper right triangle PQO. NS is the missing side, so we leave it as it is, over PQ. PQ is the line segment that we are looking for in this question, and it is equal to x. We have to find out the value of x. And it is equal to OS. OS equals to 2 units in itself, according to what is given in the question, over PO. PO equals to 3, it is the radius of the circle. So in total, if you found out that NS over x equals to 2/3. Here we multiplied the equation by x and finally found out that the missing side NS equals to 2/3 x. This is the missing side NS equals to 2/3 x units in its length. In the next step, we define this angle as beta. So in the green small right triangle SNM, this angle equals to beta, this angle equals to 90 degrees, and therefore this first missing angle must be equal to 90 degrees minus beta. Y equals 90 degrees minus beta plus beta is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees, that is the sum of the angles in any triangle. Likewise, in the big right triangle PTM, this angle equals to beta, and therefore angle beta is a common angle that belongs to both triangles. So this angle equals to beta, this angle equals to 90 degrees, and therefore this perpendicular angle must be equal to 90 degrees once beta, according to the sum rule that the sum of the angles in any triangle is equal to 180 degrees. We proved, in the next step we proved that the big right triangle PTM is similar to the small green right triangle SNN. So why those two right triangles are similar to each other? First of all, this is angle beta, that is a common angle that belongs to both triangles. So we can write down that angle beta equals to itself is a common angle that belongs to both triangles. In addition, those two angles are both equal to 90 degrees, and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees on beta, and therefore they are equal to each other. So if you prove that all the figures of the big right triangle PTM are corresponding equal to all the figures of this small right triangle SNN, and therefore those two right triangles are similar to each other according to angle similarity rule. Okay, again, if you found out that the big right triangle PTM is similar, this is the sign of similar, to the small right green triangle SNM according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side NS of the green right triangle SNM over side PT of the big right triangle PTM is equal to side SM of the green right triangle SNM over side BM of the big right triangle PTM. It has given us the question that PT equals to TS. So if we define the ref of PT as A, then TS must be also equal to A because they are equal to each other. So if we found out that from the fact that those two right triangles are similar to each other, the following relationship exists between their sides. Side NS of the green triangle NSM over side PT of the big right triangle PTM equals to side SM of the green right triangle NSM over side PM of the big right triangle PTM. We already found out that NS equals to 2/3 x over PT. PT is A according to our definition, and it is equals to MS. MS is the missing side, so we leave it as it is, over PM. PM is the diameter of the circle. The radius is 3, the diameter is 6. So PM equals to 6. PM equals to 6. So in total, we should found out that 2/3 x over A equals to MS over 6. Here, of course, multiply this equation 1, and finally found out that two-thirds x times 6 equals to ASM. 6 over 3 is 2, and 2 times 2x is 4x. So in total, this expression equals to 4x equals to ASM. So according to equation 1, 4x equals to ASM. In the next step, I repeat that quickly on rule 15, when we implemented rule 15 in our drawing. According to rule 15, if chord AB intersects with chord CD at point O, then the following equation is true, that AO over OB equals to CO times OD. So in the moment we have a circle, this is called AB, that intersects with chord CD at point O. So in this domain, the following equation is true, that AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. So we can actually implement rule 15 in our domain. Why? Because in our domain, we have chord TM that intersects with chord AB at point S. So all the requirements of rule 15 are satisfied, and therefore we can implement here rule 15. And again, in our drawing, chord TM intersects with chord AB at point S. So therefore, according to rule 15, the following equation will be true, that TS times SM equals to AS times SB. And again, according to rule 15, TS times SM equals to AS times SB. TS times SM equals to AS times SB. TS is A times SM. SM is the missing side, so it is. TS is A and SM is the missing side, and it is equals to AS. AS in total equals to 3 plus 2, that is 5, because QO is the radius of the circle, that is 3. OS is 2, so in total AS equals to 3 plus 2, that is 5, times SB. SB is 1. And again, AS is 5 and SB is 1. So in total, if we found out that according to equation 2, ASM equals to 5 times 1, that is 5. So according to equation 2, ASM equals to 5. But according to equation 1, we only found out that ASM equals to 4x. So we have two different equations for ASM. Don't forget that equation 3 that says that ASM according to equation 1 must be equal to ASM according to equation 2. ASM according to equation 1 equals to 4x. And it must be equal to ASM according to equation 2. ASM according to equation 2 equals to 5. So in total, according to equation 3, we found out that 4x equals to 5. Here we divided this equation 3 by 4, and we found out that x equals to 5 quarters. 5 quarters is 1.25. So if we found out that the length of measurement PQ is equals to x, it is equals to either 5 quarters units in its length, or in terms of numbers, PQ is equals to x is equal to 1.25 units in its length. Okay, thank you very much.